Thank you, Lee and Ellen and Joel, for the opportunity to speak today and for all the support you give in Nectar. My name is Charlie Dixon, and I worked from the beginning in Nectar and came from the deep south. Co-presenting with me are Stuart Hamilton, who is the roving design lead in Nectar, who comes from Oricon, and Cameron Payton, who became the 12D administrator and is from Riley Consultants. Let's start by giving some background to our presentation. I will be talking about the Kaikoura and its effect. Stuart will follow with an overview of the systems and survey and design. And Cameron will complete the presentation with his story of life in the Nectar world. The 2016 Kaikoura Earthquake was a magnitude 7.8 earthquake in the South Island of New Zealand. It occurred 2 minutes after midnight on 14th of November 2016. The earthquake started at 15 kilometres northeast of Culverden and 60 kilometres southwest of the tourist town of Kaikoura at a depth of approximately 15 k's. Note that Kaikoura is famous for its whale watching. Ruptures occurred on multiple fault lines in a complex sequence that lasted for over 2 minutes. Magnitude 7.8 is an enormous earthquake. It's around 32 million joules of energy which was released in those 2 minutes. That's equivalent to about 8 million tonnes of TNT. That amount of energy could power the city of Christchurch for 3 years, or every home in New Zealand for three months. Tragically, 2 people died in the earthquake. I have a short video clip that will bring some context as why an alliance was created to tackle the damage created by the earthquake. The earthquake caused significant damage to the area, closing both State Highway 1 and the main North Rail line between Picton and Christchurch. The major event disrupted lives of many. Homes were damaged, businesses were closed, farms left with damaged land and no access to markets for their goods, communities devastated by the loss of trade from passing traffic and tourists. Most feelings regarding feedback from Kaikoura is the isolation, since the state highway were closed immediately after the earthquake. With close to 1 million cubic metres of rock and material falling onto the coastal transport corridor, Kaikoura and the surrounding rural communities were cut off. In the initial response, there were over 35 groups, which included Defence Force, Royal New Zealand Air Force, Urban Search and Rescue. The New Zealand Defence Force, supported by warship HMS Canterbury, and including military and commercial helicopters, began the evacuation of more than 1,000 people. The only way in until the inland route was fixed was by helicopter or by boat. On my helicopter flight was a doctor and a psychiatrist. Funny enough, the psychiatrist did pick up I was pretty nervous, and she did comment that she had plenty of drugs to help if I needed any help. On arrival was the number of choppers that were coming and going. 24 hours, the noise, something like out of Apocalypse Now. All I needed was to have Wagner's Fifth playing Ride of the Valkyries. I worked with Kaikoura District Council evaluating asset damage. Incidentally, the American warship USS Sampson and others were in New Zealand for naval celebrations, so they were right there at the time of needed response. Part of the response was for civil defence to supply engineers, technicians to support the Kaikoura, a real hub of energy of all sorts in civil defence. Work crews worked from both ends to ensure a link road to Kaikoura was open. This allowed military vehicles to travel the still damaged inland route to carry supplies. Nectar was born. Nectar, the North Canterbury Transport Infrastructure Recovery, was set up by the government late 2016 to restore the earthquake-damaged infrastructure between Picton and Christchurch. The vision, moving mountains to reconnect communities, the founding principle of Nectar. Nectar is an alliance partnership between the New Zealand Transport Agency, Kiwi Rail and 4 key contractors, Downer, Fulton Hogan, Heb Construction and Higgins. Similar to the model set up for Christchurch earthquakes called SCIRT, systems and processes already created in SCIRT were able to be replicated and tweaked for inside the Nectar environment. Due to complex repairs in the transport system, it has been estimated that the rebuild cost of over $2 billion. The Nectar Village was created to ensure accommodation wasn't an issue for the number of contractors required to work along the State Highway 1. Each of the units is 51 squares approximately. It has 4 separate bedrooms and each with its own ensuite. The village includes recreational facilities, dining hall, laundry and gymnasium. 300 people can be housed in the village with the ability to increase if required. The initial construction techniques included helicopters and abseilers. Incidentally, I've got a wee video clip on these abseilers and I think you'll find it quite fascinating. They were used to sluice and make the slips safe. Generally the safer method of attacking the type of slips that littered the areas of damage. That 1 million cubic metres of slip material to be cleared with excavators and construction machinery. With this type of project, design and construction happened at the same time. Once the slips were cleared, repair and construction of the rail and road corridor could begin. Focus then could be on repairing of the tunnels, bridges and roads. More than 200 areas along State Highway 1 were affected by the earthquake. About 700,000 cubic metres, that's about 280 Olympic-sized swimming pools of loose material dislodged by the earthquake fell onto the road and rail. More than 30 slips were identified south of Kaikoura and the 9 major slips north of Kaikoura. Road access was quickly restored to Kaikoura via the inland route, Route 70, and on State Highway 1 south of the seaside town before Christmas 2016. Ongoing work and issues with flooding and additional slips have seen travel disrupted on both these routes through 217 and 218. The closure of State Highway 1 cost the freight industry approximately 2.7 in additional expenses per week and cuts the annual tourism of Kaikoura. Post-earthquake, the immediate challenge was diverting the drivers from the closed State Highway 1 between Christchurch and Picton to the alternate route. These roads are narrow and winding in places with single-lane bridges and an alpine pass which can be treacherous when wet and particularly during the winter months. Vehicle numbers on this route quickly rose fourfold to 4,500 vehicles per day, with 1,000 of these being heavy vehicles, up from 350 pre-earthquake. These increased traffic volumes impacted not only the road, but also local communities. New speed limits were introduced to improve safety for both motorists and communities. A $60 million improvement program developed to upgrade the road so it could handle the extra traffic. The priority was to restore access to communities that were cut off by the earthquake damage and establish a safe and reliable alternate route. The inland route 70 via Waiford and Mount Lyford was identified as the best way to re-establish the access to Kaikoura quickly. Crews worked around the clock to make the Severely road safe for general use. This included clearing the road of more than 50 slips, stabilising slopes, repairing damage, and building an entirely new diversion road. Access through this route was restored within a few days of the earthquake to allow New Zealand Defence Force convoys to get through with emergency supplies to Kaikoura, which were isolated by the slips. The main North Line railway between Picton and Christchurch is a critical part of the transport network for moving freight between the North and South Islands. Before the earthquake, about 1 million tonnes of freight travelled over the line each year. Along this line, nearly 900 sites sustained damage, including tunnels, bridges and embankments. The line was buried under more than 90 slips and landslides, 59 bridges and 20 rail tunnels were also damaged. The main North Railway line was reopened in the middle of 2017. That's quite a feat. The Kaikoura area is often referred to as where the mountains meet the sea. The transport network runs along a narrow coastal corridor with some narrow sections where the hillside hugs the Pacific Ocean. While this offers spectacular views, it is also exposed to rapid weather changes. Rebuild work has been interrupted several times because of the weather and seismic activity. Tropical cyclones Debbie and Cook hit in April 2017. This heavy rainfall resulted in further damage and work had to be halted for a number of days as more rock and material fell from the already damaged slopes. Working in such a dynamic environment has been a challenge throughout the recovery. Huge efforts have been made to protect and restore Kaikoura wildlife, which includes the largest environmental team seen in New Zealand construction project. Over 11,000 seals, many repeat offenders, have been moved by seal handlers. I've got a short wee video after this last piece I talk about, so I think you'll find that interesting. Seal handlers normally working in the 24-hour shifts to match the schedule of Nectar's roadworks program. Also, the rare Ohau rock daisy only grows in the bluff around Ohau Point. Abseilers collected plants around the point which have been successfully germinated in Nelson for planting in autumn. After this short video clip, I'll pass on to Stuart and Cameron, whom will talk to you about the survey setups, processes and systems.
NCTIR fault, a few kilometres south of the Clarence River Bridge on the Kaikoura coast. Looking here at the fault plane, the plane of movement along the fault itself, where this side here has moved up by about 1.5 metres, and we can see the gravels here and the gravels on that side. But what's really interesting is that we can see lines of movement here on this fault plane which are moving down a little bit in this fashion. And that means we can see, it looks impressive that we're standing here 1.5 metres high, but in fact most of the movement has been along a plane something like this. So this side here has moved forwards by many, many metres. These fault scarps form very, very quickly. And we know from earthquake physics that probably this fault scarp ruptured across here at a speed of about 3 kilometres a second. So this has uplifted a very large area of new reef here, and the locals here describe not the earthquake noise, but the noise of water running off the top of this uplifted platform here. They said that the noise was just horrendous. And on the downthrown side of the fault, it's actually still even come up by about 1.5 metres. On the other side, there's as much as 6 metres of uplift.
There's still one under there.
Okay, yeah, and that little pool.
Yeah, you see it down there?
Yeah.
And then that's it, something like
That one and come out.
so just keep the water out of it.
Hello and thank you, Charlie. My name's Stuart Hamilton and I'm a senior civil designer with Oricon based in Christchurch, New Zealand. I've been a 12D user for around 20 years where I've designed everything from state highways to subdivisions, underground infrastructure, cycleways, irrigation dams and much more. In recent years I've been involved as well as administration in the 12D Synergy. But that's not why I'm here today. Since July of last year I've been seconded to the design team as part of Nectar, as the roading and 12D design technical lead. There have been plenty of challenges along the way, but we have seemed to overcome them with some lateral thinking, technology and the support of 12D solutions. So what have some of the challenges been? As Charlie mentioned, this was one of the most complex earthquakes ever recorded. To put it lightly, it belted the South Island, shook the rest of New Zealand and was estimated as a 1 in 5,000 to 1 in 10,000 year event. So as a starting point, Mother Nature had laid down the gauntlet and it was up to Nectar to work around her and get the transport network operational and Kaikoura open again. So, what were some of these challenges? Uncoordinated survey network. The network of survey benchmarks along the coast and the surrounding areas was completely out of alignment and would need to be recalculated. Accessibility to the sites. The quake had blocked the roads, brought down material. This was very unstable and would mean access was going to be tricky, not only from a physical sense, but also a health and safety point of view. Risk of rockfall. The quake had dislodged many large rocks, with plenty more rocks hanging around above the road and rail that were looking for opportunities to roll down the hill. How to capture the terrain. The road and rail was wedged between the Pacific Ocean and the Kaikoura Ranges, with cliffs rising steeply 200 to 300 metres above the coastline. How to manage and distribute the data. The amount of data that this project was going to generate was unknown. The data was needed to be managed as well as means to manage the design process and the rapid changes that were going to occur throughout this project. So how did we deal with them? The uncoordinated survey network. In terms of this, Australia, you're currently implementing your new geocentric datum to take into account 1.5 to 1.8 metres of continental drift that occurred in 26 years. Wow. At Nectar, the survey team had to take into account tectonic movement, which had moved things up to 12 metres in 74 seconds. So, a revised local survey network was developed and incorporated into a survey specification that was provided to the contractors who went out to capture the survey data, and I think some of them are here today. The survey specification outlined the definition of the survey network, the requirements on how various elements should be captured, and how the data was to be delivered to Nectar. This was important as the survey team had workflows that processed this data into 12D master projects, which formed the underlying base data for the rapid design process that was underway. Having the data in a predefined structure allowed the chains to process the data and have it available. How to capture terrain. As many of the sites had limited or no access, the old chainperson and staff was not really going to work for a lot of these sites. Just after the survey, aerial LiDAR and photography was flown along the corridor to provide a basis for moving forward. LiDAR surveys have been repeated several times over the project lifetime and are building a picture of the coastline as it has evolved over 18 months. We couldn't really give up on traditional survey methods, and these have been used for establishing the control, filling in areas of specific requirements, and setting out of the construction projects, which made getting the underlying coordinate system right. Vehicle-mounted laser scanning has been used during the project, with a vehicle driving the length of the corridor capturing as much data as possible. This, combined with a panorama camera mounted to the vehicle, has given the design team at Nectar effectively a street view every run. Ground-based laser scanning. Scanners have been used in tunnels and other areas to collect data, detailed point clouds. These point clouds have been incorporated into the design and many tunnel repairs. Hydrographic surveys of the seabed have been carried out to understand the effect of the quake on the seabed and the potential changes to the coastal processes. And UAVs have been used along much of the coastline to capture slip sites and other hard-to-get areas. These have provided an excellent means of getting data without putting people into areas that were still potentially unsafe. Here are a couple of examples of the scanning that we've had. From a design perspective, these have been, having this information on hand has been incredibly useful. And as a side note, that's what happens when a tunnel goes through a quake zone. That is a rail tunnel that had laterally half a metre of movement right through the Hope Fault. So, how did we manage the data? Network drive was the perfect choice. It had been used for many years, had a common interface, and was a place that needed a little setup. However, it did have its drawbacks. With no real document management, required permanent connection for remote users, and these sort of really all counted against our use of a network drive. Having said that, we are still using a network drive as some of our workflows. GIS. Another option was a GIS platform. However, this yet again did not meet the design tools requirements. Having said that, the GIS system that Nectar has developed forms a major part of our project and provides the team with extremely valuable information. Within the GIS system, we have access to client assets, property information, live site reports, road and rail features, and much, much more. We have developed workflows to publish data from 12D so that it can be seen by non-12D users in the GIS space. This has proven valuable, especially in meetings when 12D designers are not available. General users can overlay different bits of information from the layers in combination with the design strings from 12D. The GIS system is utilising the network drive and reads some of the raw data that is provided from various Nectar sources. But in the end, it was decided a document management system was needed. The question was which one to use. Nectar was already using a document management system for the construction team, however this yet again did not meet our requirements. Given we were already using 12D model, for the design side of things, 12D Synergy would be the perfect fit and was selected as the preferred design document management system. Within the Synergy, we are supporting many systems. All 12D projects are hosted within Synergy. Calculations and report specification emails and many more documents are managed in this system. Drawings, yes, we're using AutoCAD, are hosted, updated and managed within Synergy. Yet again, we have drafting staff working in different parts of the world working on drawings in coordination with the teams in Christchurch. We even have Revit users who store their final models within Synergy to ensure all the project data is in one location together. Pretty much any file that is created as part of the design process are stored within Synergy. This includes things like templates and configuration files, that then made available for users. So, the Nectar system. After it was chosen, it's been running for about 12 to 18 months, and here are some of the numbers that we are using at the moment. As of last week, we had 240 plus users actively using Synergy. We peaked last year with around 350. Over 100 of those users have been external to the design office in Christchurch, working in New Zealand, Australia and around the world. There are approximately 1,200 jobs in the system with an excess of 600 12D projects. There are currently 1.1 million files with 1.8 million file changes to these files, with an excess with 4 terabytes of data changes in the system. The system has ensured we had a single point of truth for our design and documentation. Overall, users have enjoyed working in the Synergy environment, especially when they have to roll back because of an issue or a change in the design. Synergy has allowed our process to evolve as the project has morphed in complexity. The beauty has been that required changes have had little impact on the day-to-day users. It is nice to see that some of the things that we have developed workarounds for at Nectar are being incorporated into the 12D Synergy 4, and these would have been very handy on many occasions. When all of the systems are brought together, the data management on this project is a little mind-boggling. Given the project is around 18 months old, Nectar is currently working with 9 terabytes of data, and that is the data we're provided. It doesn't include all the pre-processed data that comes to us. So, as a sort of a design and construction, here's a few examples of some of the projects that have come out from our system. A fast bridge. The construction team delivered the fastest multi-span bridge to be constructed in New Zealand, with a 7-span, 144 metre long iron gate bridge constructed in just 14 weeks from ground up. This was in addition to 3 other single-span debris flow bridges further along the coastline. In total, 120 24-metre long bridge beams had to be transported from around the country along roads that were not designed for vehicles longer than 30 metres. There were 2.5 kilometres of seawalls which were constructed, with many of these foundations starting in the middle of winter in 2-hour windows that aligned with low tide day and night. At one point, the Nectar project was consuming all of the available cement in New Zealand. From a digital development point of view, augmented reality has been utilised to provide the tunnel construction team with a digital milling picture of work that is required within 4 road tunnels. The tunnels were modelled in 12D using an original scan data provided. Tri-mesh profiles were created using 12D snippets, and then through some third-party processing published onto iPads. The crews were able to walk along and get an idea of where the material needed to be removed. Safety has been probably, and the biggest goal was opening the road. This was to get the transport network open again and reduce the demand on the alternate route, which had never been designed to carry the additional traffic. It has also meant getting the town of Kaikoura open, ready for business. On the 17th of September 2017, the first freight train since the quake travelled along the corridor. Then on the 14th of November, exactly 1 year after the quake, the harbour was reopened for business, which allowed one of Kaikoura's main attractions, whale watching, to return. Then on the 15th of December, 1 year, 1 month and 1 day following the quake, the road was opened to daytime traffic. This was then followed by 24/7 operations returning to the road at the end of May this year. The story of Nectar does not end here, as the project has another 1.5 years of design and construction to complete. I'm sure there will be more stories that will come in the following years about this project. Oh yeah, how do we deal with the Rockfall Risk? Well, there was scaling, helicopter monsoon buckets, water cannons and other attempts, but sometimes these rocks just didn't want to move and the Mythbusters approach was taken. Hopefully it works.
NCTIR fault, a few kilometres south of the Clarence River Bridge on the Kaikoura coast. Looking here at the fault plane, the plane of movement along the fault itself, where this side here has moved up by about 1.5 metres, and we can see the gravels here and the gravels on that side. But what's really interesting is
Rocky. That one there. So this was Rocky. It's a 200 plus rock that sat above the workers for over a year that many people had commented about when driving past. Needless to say, Rocky is no more. After 35 kilograms of explosive were used to dislodge him from his hillside residence. His partner, Millie, had suffered a similar demise at the end of 2017. Myself and the Nectar team would like to thank Lee, Alan and Lane, along with your teams, for the ongoing support that you have provided Nectar as the project has progressed. Has been very much appreciated. I can honestly say that your help has enabled Nectar to move mountains and reconnect communities. Thank you. I would like to now pass over to Cameron Paynton, who's going to talk about his role and some of the design processes at Nectar.
Thanks everyone. As Stuart said, my name is Cameron Paynton and I work for Riley Consultants. I've been a civil engineer for about 5 years now and been using 12D since the start of it. I'll be talking about my sort of journey through Nectar and also to sort of explain the design and construction process at the same time. Oh, Stuart, that's me. Cool. So I came into Nectar in the start of April 2017. The 12D team was already pretty developed in the geometric space for the road design. So I was coming in to provide support to the geotech team, cutting cross sections through slopes for rockfall modelling. It was pretty basic stuff, but it was a good way to understand the project as I was cutting cross sections along the entire length of the coastline, from Site 32 in the south all the way up to Site 9 in the north. And there was a slightly confusing naming convention where Kaikoura was home base, and as you worked out from Kaikoura, you had Site 1 in both the north and the south. So it was a good way to understand the project because people were referring to Site 1, P1, S1, all this different stuff. And I was sort of using 12D in a slightly different way than what Nectar was set up. So in Synergy, we had each individual site had its own sort of synergy job, but I was wanting to share in stuff from multiple master projects across many different jobs, which meant I was sort of constantly challenging the system support team of Dan Winter and Charlie and the survey team, just trying to make my own special project which brought all the data in. This sort of pestering of the system support was a running theme throughout my time at Nectar. The cross-section work wasn't enough of a workload to justify me being there full-time, so also had a small job for a stormwater engineer modelling box culverts to go under the road, just south of Ohau Point at 3 locations. The purpose of these 3 by 3 metre box culverts was to pass debris flows through them and underneath the road and rail. This job suffered a little bit of scope creep as the debris flows were less than a concrete slurry consistency and more of a boulder and tree consistency. So that's me there. I'm about 2 metres tall. That rock is a little bit bigger and wider than me. Some of the rocks coming down off the hillside were about the size of caravans, and the tree trunks coming with it were 5 to 6 metres long. So a 3 by 3 box culvert wasn't really going to cut it. So more of these debris flows kept cropping up. Pretty much whenever we had a heavy rainfall, there'd be a new slip appear. So the sort of the progress we were making on site was constantly being knocked back. The 2 cyclones which hit the coastline in Easter 2017 brought quite a lot of extra debris flows down. I've modelled dams in 12D back in my home organisation. So I knocked out a few conceptual designs of bunded areas to capture these flows, drain the water out of them, and then go in later with earth moving equipment to remove the rock. So this is one of the sites here. That's the source area. We're about halfway up in a helicopter. It's about 200 plus metres tall. And the amount of material sitting up in there was going to take 5 to 6 years to come down based on the rainfall we were getting. So the plan was to direct the flow, instead of coming this way and over the road and rail, direct it round to the side and into this bunded basin area. This is another bund that we put in to sort of protect the state highway, and here's some pictures from the site. So up there, that's the source material, and get a bit closer. So those are fully grown trees sitting there, and pretty much the top of the slit was just sort of coming off in big wedges and then coming down in the rain. Back to those box culverts. So this was what the sites looked like, a lot of muddy debris coming washing down. This is sites sort of 4 and 5, where these debris fans were coming out, and this is site 6, just south of Ohau Point, where that large boulder was that I was standing next to. And this is the source area of the material which is sitting up there, which is going to take probably 5 to 10 years, we estimate, to come down. So we proposed putting in some temporary bridges, like Bailey bridges, but they were speed limited to 30 kilometres an hour, so that wasn't really a permanent solution for a state highway. So we opted for some permanent bridges. So this is probably one of the first conceptual designs. This is the final product. This is the 2 sites. Couldn't get the raster to drape on this tin, so I just had to grab it without. But you can sort of see the fan of material which is building up here. And it was a total road vertical realignment, and we also had to retain the rail embankment. I also took over a road and rail alignment from someone who left the project about a month or so after I arrived, unrelated, and so I got stuck into the road realignment. So he'd already done the rail, which was a bit unfortunate because the rail was on the outside and the slips were on the inside, and I had to fit the road in between the two, so I was sort of constrained by previous design decisions. So this is site 1 in the north. It's got 2 slips here, slip 1A, slip 1B, and pretty much the design was to put walls in front of the slips with access behind so you can remove material, and nice big sort of coastal protection riprap to stop the rail from eroding. So this is looking at the start of site 1A, it's about 5 metres tall. So just mass concrete blocks linked together, sitting behind this, which would absorb the impact from the rock falls, so they say. And this is the road which kind of got squeezed a bit between the rail, which was already built, and the slips. This is sort of midway, that's site 1A, that's site 1B. And we have a bunch of stormwater to take the water from over here and out to sea. And this is at the northern end, so it was about 1 kilometre long. Quite a good project to get involved in. So through this project, I realised there wasn't a consistency in the output across the 12D geometrics team. Different long section plots, DWG outputs, CAD wasn't going onto preset layers, the naming convention was out of date. So Dan Winter, he was responsible for all of this, but he didn't have time to deal with the backlog of 12D model changes because he was also migrating the Nectar design team onto Synergy. And he got a bit sick of me pestering him, so he gave me the job to do it instead. So I suppose the motto was, don't pester people too much or they'll just get you to do it yourself. So this is the design process in the centre. So the simplified design process at Nectar. So the survey and asset information is captured by field surveyors in Kaikoura in a shorthand code. It's processed by the survey team in Christchurch into a longhand code and saved in the central engineering database master projects. The designers share in the data from the master projects and design based on agreed naming conventions. They export their designs into DWG format in plan and section plots for drawing production in AutoCAD, and export the 3D design strings and tins in 12D format to the survey team in Christchurch. The survey team checks that the design matches the naming convention before remapping it into field survey shorthand, to allow the field surveyors in Kaikoura to set out the design and the contractors to build it. So the overall role of the 12D systems administrators to work in these two sort of boxes here, make the design process run smoothly and efficiently inside 12D and when exporting from 12D. This is especially important on the Nectar project because we were time constrained, not cost constrained, which was quite unique. The overall philosophy was to keep the modifications we made as lightweight as possible, only customise files where needed to make it easy to walk away from this and have someone else pick it up. And also if 12D had a major update, we wouldn't have to do a bunch of work to keep things running. So I started on clearing the backlog, updating or creating files in the user and user lib folders to ensure consistency throughout Nectar. I reduced the drainage footy file down a lot, sorry Charlie, to stop the confusion amongst designers and speed up plan and long section. So instead of having 3 different pit types for the same pit, we just had one. And that really helped going into CAD as well, because then we could do your long section and plan plots of that. I created a bunch of plot PPF files for long section and cross sections, for road and rail alignments. Eventually you could export from 12D as into a DWG XREF. It would appear in the drawings in the correct layers with the correct colours and line styles, and there would be very minimal edits required by the caddies. So it really sped up the whole drawing production. Once I cleared the backlog, I worked on requests from the design team and other things such as a chain to publish the 12D data into the GIS, and also for visualization, which I'll just show you a few things. So this is Ohau Point and 12D visualization. Looks pretty good, but unfortunately we went to another package to spruce it up to the next level. So this is the final product. That's Ohau Point over there. So these were used for public facing stuff. And also I think a bit of VR as well for the clients. And then just back to my sites. This is site 1 in October, 5 months after my site visit there. So the slips are still there, and building the buns in front of them, and the rails there, and the road is about to have its asphalt laid. And then the debris bridges. So this is debris bridge 4 and debris bridge 5. So they're under construction. And this is sort of looking over back along Half Moon Bay. So the reason I was out there was we were looking at all the source material sitting up in there, which was kind of wanting to come down between the 2 bridges, which would have been a bit embarrassing. So we were trying to train it to go either side into the 2 channels. And then this is Ohau Point under construction, looking from site 7. So pretty massive thing. And this top third of the hill is covered in a chainmail mesh to stop rocks pinging off it. So that's it. Just got the 12D slides at the end. I'd like to thank everyone for listening to us, and if you've got any questions about the Nectar project, come see myself, Stuart or Charlie in the morning tea. Thank you.